Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. This is my fourth video on linear independent sets and basis. In this video, let us quickly recap some of the definitions which are used in solving the problems today. Recap the definition of linearly independent and dependent sets, the definition of basis. Later we move on to solve problems on basis and problems on basis of null A and problems on basis of column space. So these are the things which we are going to do today. So let us first recap the definition of linearly independent set. An indexed set of vectors, set of V1, V2 and so on Vp in a vector space V is said to be linearly independent if the vector equation C1 V1 plus C2 V2 plus so on plus Cp Vp is equal to O, the zero vector, has only the trivial solution. The trivial solution is C1 is equal to 0, C2 is equal to 0 and so on Cp is equal to 0. So if the vector equation C1 V1 plus C2 V2 and so on plus Cp Vp is equal to O, the zero vector has only the zero solution and no other solution, we can say that the set of vectors V1, V2 and so on Vp as the linearly independent set. In contrast, the set of V1, V2 and so on Vp is said to be linearly dependent if the relation which we call as linear dependence relation C1 V1 plus C2 V2 and so on Cp Vp is equal to 0 as a non-trivial solution. If we are able to find a non-zero solution for this equation, then we can say that these vectors are linearly dependent. That is, there are some weights C1, C2 and so on Cp, not all zero, such that this relation holds C1 V1 plus C2 V2 plus so on Cp Vp is equal to O. So if we are able to find a non-zero solution for this relation, we say that the set is linearly dependent. If we are unable to find a non-zero solution, then we can say that the set is linearly independent. And this is the linear dependence relation. C1 V1 plus C2 V2 and so on, Cp Vp is equal to 0. When we can find a non-zero solution for it, then it is called a linear dependence relation among the vectors V1, V2 and so on. And basis, let H be a subspace of a vector space V. An indexed set of vectors B is equal to B1, B2 and so on Bp in the vector space V is a basis for H if the two conditions. First one is B is linearly independent set and second one is B should span H. That is H is equal to span of B1, B2 and so on. If these two conditions are fulfilled, then the set B is said to be a basis for H. If we can find a set such that it spans the entire vector space V and it is linearly independent, then we can say that that set is a basis for the vector space. So we have gone through these theorems. Let us quickly go through the statements. An indexed set V1, V2 and so on Vp of two or more vectors with V1 not equal to O, zero vector, linearly dependent if and only if some Vj with j greater than 1 is a linear combination of preceding vectors V1, V2 and so on Vj minus 1. So whenever a set is linearly dependent, we can find a vector Vj such that it is a linear combination of preceding vectors. Of course, obviously j is greater than 1. And other condition is the first vector in the indexed set v1 should not be the 0 vector. And whenever we can find such Vj, which is a linear combination of preceding vectors, we can say that the set is linearly dependent. And this is spanning set theorem. Let S is equal to set of V1, V2 and so on Vp be a set in a vector space P, and H is equal to span of V1, V2 and so on Vp if one of the vectors in S, say Vk, is a linear combination of remaining vectors in S, then the set formed by S by removing Vk still spans H. So there will be no loss if a vector which is a linear combination of other vectors is removed. And part B is that if H is not a null space, some subset of S is a basis for H. When H is equal to span of V1, V2, Vp, that is S. So it guarantees a basis whenever H is not a null space. And H is equal to span of some set S. And finally, this is one more thing. We have seen that the pivot columns of a matrix A form a basis for column space A. So pivot columns are the columns in which pivot positions exist. So only pivot columns of a matrix A can form a basis for column space A. These are the statements which we have proved in earlier classes, and we are going to use these results in today's problems. So this is what happened so far. And we have seen this one also, enlargement of sets. So a basis can be extended, then it will not span, it will span Rn, but its property of linearly independence will be lost. If a basis is extended and one more vector is added to that one, then the set will become linearly dependent. If we shrink a basis, remove a vector in basis, it cannot span the vector space. So from this we can say that all the number of vectors in all the bases are equal. You can replace the vectors of the basis, but you can't add or remove without replacing to form a basis. So let us look into the problems today. This is the first one. Determine whether the set containing 100, 110, 111 is a basis for R3. So three column matrices are given, which are vectors of R3. We have to check whether the set containing these three vectors is a basis for R3 or not. If it is not a basis, check whether the set is linearly independent and whether it spans R3. Of course, if these two properties will hold, then only we can say that it is a basis. If it is not a basis, any one of the property may hold or may not hold. So let us name the vectors. Let v1 is equal to 1 0 0 and v2 is equal to 1 1 0 and v3 is equal to 1 1 1 for our convenience. And let A is equal to matrix of v1 v2 v3. So using these three vectors, column vectors, let us form a matrix A. So A is equal to 1 0 0 1 1 1 1 1 1 as columns. So it is now in echelon form. The matrix form A is in echelon form, and we can observe that there are three pivot columns. This is the pivot position, first pivot position, second pivot position, and third pivot position. So this column is known as pivot column. This is also another pivot column. This is another pivot column. So there are three pivot columns in A. So first of all, we need to form a matrix using the given vectors, and then we have to convert it into echelon form. But here the matrix is already in echelon form. Clearly we can find the pivot positions. All the three columns are pivot columns. So there are only three rows. All the rows contain a pivot position. So here the first row, in the first row this is the pivot position. Second row this is the pivot position, and third row this is the pivot position. If we look into it at the column wise, in the first column this is the pivot position, so this is the pivot column. In the second column this is the pivot position, so it is the pivot column. Similarly this one is the pivot position and this is the pivot column. So each row of A has a pivot position. So whenever each row of A has a pivot position, we can say that the columns of A span Rn. Here Rn is 3. So columns of A span R3. All columns of A are pivot columns. So they are linearly independent. Whenever all the columns of a matrix A are pivot columns, we can say that all the column vectors are linearly independent. So in this case, the vectors, column vectors are both they can span R3 and they are linearly independent. So both the conditions of a basis are satisfied. So we can say that these vectors, these columns of A form a basis for R3. Columns of A are nothing but the vectors, given vectors. So set of V1, V2, V3 is a basis for R3. There may be many bases for R3, but this is one of the basis for R3. So this is the first problem. So we can conclude that if number of pivot positions is equal to in a square matrix, particularly in a square matrix, is equal to n. If in a square matrix n by n, the number of pivot positions are n, then the columns form a basis for Rn. Of course, that is one of the result of invertible matrix. So here we have three pivot columns. which are formed in a 3 by 3 matrix. So these three can form a basis for R3. This is another problem. Determine whether the set containing 1 1 0 0 0 0 0 1 1 is a basis for R3. If not, check whether the set is linearly independent, whether it spans R3. So here we can observe that the middle one is a zero vector. So any set which contains a zero vector is linearly dependent. A linearly dependent set cannot form a basis, so it is not a basis. Clearly, we can say that. But let us solve the problem in Algebra manner. Let us name the vectors. Let v1 is equal to 1 1 0 and v2 is equal to 0 0 0, the zero vector, and v3 is equal to 0 1 1. And let a is equal to v1 v2 v3. That is 1 1 0 0 0 0 and 0 1 1. So it is not in echelon form. In echelon form, all the entries below the leading entry must be zeros. So here, this is the leading entry, but this is not a zero. So let us reduce this matrix into echelon form by applying elementary row operations. So this can be converted as 1 0 0 1 0 0. First row is as it is. So I am performing R2 minus R3. Will give you R2 minus R3. So 1 minus 0 is 1, 0 minus 0 is 0, and 1 minus 1 is 0. Third row remains same. So this matrix can be converted as this one. Here we can see that these two are same. So I can subtract R2 from R1 so that it will become a zero row. 1 minus 1 is 0 and remaining two are also zeros. By interchanging these two rows, I can take the zero row below the non-zero rows. So now this is in the last one is in the echelon form and even in the reduced echelon form. So for these problems, echelon form is enough to us. So now this is in echelon form. So now in this matrix, which is equivalent to the given matrix formed by given vectors, there are only two pivots, this one and this one. So now this matrix is in echelon form and has two pivot columns. Only these two are 1 and 3 are the pivot columns. So third row, this is the third row. Third row does not have a pivot position. So there is no pivot position in this third row. So the columns cannot span R3. So whenever a row is full of zeros, and it is a zero row, it cannot span Rn. Here it cannot span R3. Since using the first two, using these columns, we can't produce an element other than 0 in the R3. So any vector with a non-zero entry in the third row cannot be written as a linear combination of these vectors. So it cannot span R3. So the columns of A cannot span R3 since this is equivalent to the given matrix. Since we are performing only elementary row operations, the dependence relation will hold. The same dependence relation will hold in A also. So if we cannot produce all the elements of R3 using this matrix, we can't produce all the elements of R3 using A3, using the vectors in A also. So columns of A cannot span R3. For the convenience, I have taken this here. This is the given matrix and this is the reduced echelon form. Here we can observe that second column of A is not a pivot column. It does not contain a pivot position, so it is not a pivot column. So whenever it is a non-pivot column, all the non-pivot columns are a linear combination of preceding columns. So of course this is a zero vector. This can be written as 0 times this one. Or any for any scalar. So it is a linear combination of preceding vector, or you can use these two to get this one. So it is a linear combination of vectors. So columns are linearly dependent. Whenever you find a zero vector in a set, that set must be linearly dependent. So given vectors cannot span R3 and are not linearly independent. So both the properties fail in this case. So columns of A does not form a basis for R3. Or the given vectors V1, V2, V3 is not a basis for R3. Let us look into one more example. Determine whether the set containing 1, 0, minus 3, 3, 1, minus 4, minus 2, minus 1, 1 is a basis for R3. If not, check whether the set is linearly independent, whether it spans R3. Name those vectors. That V1 is equal to 1, 0, minus 3, V2 is equal to 3, 1, minus 4, and V3 is equal to minus 2, minus 1, 1. And let A is equal to matrix of V1, V2, V3. That is 1, 0, minus 3, 3, 1, minus 4, minus 2, minus 1. So we are forming a matrix using the given column vectors. Here A is not in echelon form, and it can be reduced to echelon form by performing elementary row operations. So we need to make it 0 first. Later we need to find a leading entry here, root position. So let us perform the elementary operations. This is the given matrix, and the first row is as it is, second row is also altered, and in the third row we are adding 3R1 plus R3. R3 goes to 3R1 plus R3. So 3 plus 3 minus 3 is 0. So minus 4 plus 9, that is 5. 1 minus 6, that is minus 5. So 5 minus 5, so we can divide the third row with 5, so that we can get 0, 1, minus 1. These two rows are same, so I can subtract this from R2. So I will get all zeros in the third row. Now this is in echelon form. So this is a pivot position, and all the entries below this pivot position are zeros. And to the right, this is another pivot position, and the entries below it are 0, and there is no pivot position. So there are only two pivot positions. So there are only two pivot columns in this matrix. So now it is in echelon form, and it has two pivot columns, 1 and 2. First two columns are pivot columns. Third column is not a pivot column. And further you can observe that third row, this row, does not have a pivot position. So it does not have a pivot position, and third column is also not a pivot column. Whenever a row does not contain pivot column, we can say that the columns of A cannot span R. For the same old reason, we can't produce non-zero scalars in the third row using this matrix. So columns of A cannot span R. So third column of A is not a pivot column. So third column can be represented as a linear combination of preceding vectors. It can be written as linear combination of preceding vectors. So these three columns are not linearly independent. They are linearly dependent. So columns of A does not form a basis for R3. In this example also, both the conditions are failed. It is neither linearly independent nor spanning the set R. So both the conditions are failed. So the vectors, the given vectors V1, V2, V3 is not a basis for R. Let us look into one more example. Here 4 vectors are here. Determine whether the set containing 1, minus 2, 3, 0, 3, minus 1, 2, minus 1, 5, 0, 0, minus 1 is a basis for R. If not, check whether the set is linearly independent and check whether it spans R. So we know that whenever there are more vectors than the entries in a vector, the set is linearly dependent. A linearly dependent set cannot form a basis. So it is not a basis. Let us prove it further. Let us name these vectors V1, V2, V3, V4. Let us form a matrix using these four vectors. Let A is equal to matrix of V1, V2, V3, V4. That is equal to 1, 0, 2, 0. Entries of first row in all the vectors. 1, 0, 2, 0. Minus 2, 3, minus 1, 0. 3, minus 1, 5, minus 1. So this is the matrix formed using the given vectors. We can observe that this is not in echelon form. So we need to convert this into echelon. We need to reduce it into echelon form by using elementary operations. So again, we are making these two zeros by using elementary operations. So this row is added twice the first row. So R2 goes to R2 plus 2R1. Similarly, R3 goes to R3 minus 3R1. So after completing the calculations, we find this. Minus 2 plus 2 is 0. 3 minus 3 plus 0 is 0. Minus 1 plus 4 is 3. And this is 0. Similarly, this one. So here we can find 3, 3. So I can divide it with 3. So that I can get 1, 1. Now to get echelon form, I need a 0 here. So I am subtracting this from R. So these two become 0. So now the matrix is in echelon form. So we have 3 pivot positions, this one and this one and this one. So 1, 2 and 4 are pivot columns. 3 is a non-pivot column. For the convenience, those are not here. Now it is in echelon form and it has 3 pivot columns, 1, 2 and 4. All the 3 rows contain pivot positions. So columns of A can span R3. These columns can span R3 since all the rows contain pivot positions. But third column of A, this one, does not contain pivot position, so it is not a pivot column. When it is a non-pivot column, it can be represented as a linear combination of preceding columns. So it cannot be linearly independent. So the columns are linearly dependent. Since they are not linearly independent, columns of A does not form a basis for R. Here first condition failed. The columns can span R3, but they are not linearly independent. So these vectors, the given vectors, cannot form a basis for R3. So let us look into one more problem. Find a basis for null space of the matrix 1, 1, minus 2, 1, 5, 0, 1, 0, minus 1, minus 2, 0, 0, minus 8, 0, 16. We have already find the null space of the matrix A. We find a spanning set there. Now we are going to find a basis for the null space. You can observe that the given matrix is in echelon form. It is already in echelon form. Since the entries below the leading entries are 0, here and this is 0 again. So it is already in echelon form. So let us name this A. So this is a 3 by 5 matrix. To find the null space of A, we need to find a general solution of Ax is equal to O null matrix in terms of free variables, as we did in our previous problems. For that, let us construct a augment matrix A. O is the null matrix. So we are adding 0 entries in the last column. That is our augment matrix. So this is already in echelon form. But for convenience, we can divide the third row with -8, so that the third row will become 0, 0, 1, 0, -2. So to find whether the vectors are linearly independent or whether they can span, echelon form is sufficient. But to form a null space, we need to convert the matrix into reduced echelon form so that the equations are simplified. So now it is in echelon form again. To make it into reduced echelon form, we need to make this 0 and this is also 0. So there will be only one entry, that is also 1 in the pivot position. So already there are 1s in the pivot positions, but we need to make these 2 as 0s. For that, R1 goes to R1 minus R2. We are subtracting this from this. So it is 1, 0, minus 2, 1 minus of minus 1 is 2, 5 minus of minus 2 is 7, 0. Remaining 2 roots are as is. And now R1 goes to R1 plus 2R. So that it will become 0. So 1 plus 0, 1, 1 plus 0 is 0 plus 0 is 0, and minus 2 plus 2 is 0, 2 plus 0 is 2, here 7 plus minus 4 is 3, and 0. Remaining 2 rows are same. So now it is in reduced echelon. So which is equivalent to, this matrix can be converted into equations form. So x1 plus 2x4 plus 3x5, x1 plus this is related to x2, this is related to x3, this is x4. So x1 plus 2x4 plus 3x5 is equal to 0. Similarly, the second row gives us x2 minus x4 minus 2x5 is equal to 0. And third row gives us x3 minus 2x5 is equal to 0. This is the third one. x3 minus 2x5 is equal to 0. So the general solution is, this can be written as x1 is equal to minus 2x4 minus 3x5. x2 is equal to x4 plus 2x5. x3 is equal to 2x5. With free variables x4 and x5. In all the three vectors, we can find x4 and x5 are free variables. Now, the vector x1, x2, x3, x4, x5 can be written as x1 is minus 2x4 minus 3x5. x2 is x4 plus 2x5. x3 is 2x5. x4 is x4. x5 is x5. So this can be simplified as x4 times minus 2 and 1. There is no x4, so 0. And here x4, so it is 1. No x4, so 0. Plus x5 times minus 3 and 2. And again 2. No x5, 0. So it is 0. x5 is here, so it is 1. So this vector x1, x2, x3, x4, x5 can be written in this form. So now it is in the form of some x4u plus x5v, where u is equal to the first vector minus 2, 1, 0, 1, 0, v is equal to minus 3, 2, 2, 0, 1. So every linear combination of UV is in null space. So you can take any scalar in place of this x4 and x5. So UV, where u is equal to this first vector and v is equal to this vector, set of UV is the spanning set of null A. So these two vectors can span entire null A. And we can observe that these two are not multiples of each other. So you can't get this vector from using this one. So null A can be written as span of UV, that is span of this. Further, these two are not multiples of each other. So they are linearly independent. So both the properties are fulfilled. So I can say that these two vectors form a basis for null A. Our basis for null A is the set of UV, that is set of these two. So this is the basis. Let us check whether these are correct or not by using some more examples. I have carried that matrix here, and this is my answer. Null A. We are saying that these are the vectors in the basis for null A. Null A means these two vectors will give you zero solution. And any combination of any linear combination of these two vectors should also give a zero answer. So these entries of the given matrix are carried here. You can see this 1, 1, minus 2, 1, 5, and 0, 1, 0, minus 1, minus 2, 0, 0, minus 8, 0, 6, 2. So I have two vectors now. This is my first vector, minus 2, 1, 0, 1, 0, minus 3, 2, 2, 0, 1. So I am taking a linear combination. For example, here 1 and 1. I am adding these two. This is the resultant vector u plus v. And I am multiplying this A with this vector. I am getting a zero vector. So it is in the this vector is in the null. It is a linear combination of these two vectors. Any linear combination of these two vectors. For example, I can multiply this 5 and this -7. This is another linear combination. I will get another vector. If I multiply this matrix A with this vector, I am getting 0 vector. So any linear combination of these two vectors will be an element in null A. So these two form a basis for null space A. You can observe that if we change anything, any entry in this one, so this is my basis. Instead of 2 minus 1, I am putting another vector of 2. You can observe that this is not a 0 vector. So other than this vector, I can't use another vectors to form a basis for null A. So here I have taken some more vector. This is changed. This is not a vector in my basis. Here I should put 1 only. So this is my vector. So if I am using this for any scalar, we can get here 0 vectors. So this is a matrix multiplication. This is a 3 by 5 matrix and this is 5 by 1. So resultantly we are getting 3 by 1. So this is the example. Let us go back to our PPT. So this is one more problem. If A is equal to -2, 4, -2, 4, -2, -4, 2, -6, -3, 1, -3, 8, 2, -3, B is equal to 1, 0, 6, 5, 0, 2, 5, 3, all zeros. And it is given that A is row equivalent to B. Then find basis for null A and column space. So echelon form is readily given to us. For convenience, let us name it A. Let us name the columns. Let A is equal to matrix of A1, A2, A3, A4 is equal to given matrix. So that A1 is first column, A2 is second column, and so on. And B is equal to matrix of B1, B2, B3, B4, which is the echelon form of the given matrix. Now B is in echelon form. You can observe this. All 0 entries below the leading entry. So these two are the pivot columns. So B1 and B2 are the pivot columns, remaining are non-pivot columns. Since A is row equivalent to B, pivot columns in A are A1 and A2. These two are pivot columns. Since these two are row equivalent, we have seen the previous statement that pivot columns of a matrix form basis for column space A. So A1, A2 form the basis for column space A. Therefore, basis for column space A is set of A1, which is very simple. To find a basis for column space A is very simple. Just to convert it into echelon form and find the pivot columns. Then pivot columns of the original matrix A will form the basis for column space, but not the pivot columns of the converted matrix. You have to take the original matrix. The same pivot columns will be here. We have to collect the columns of original matrix, given matrix. So this is the basis for column space. To find the null space of matrix A, as we did in the earlier problem. We need to find a general solution for Ax is equal to O. So the augment matrix AO is equal to this one. We are adding zero entries in the last column to the given matrix C. So that is equivalent to BO, since B is the echelon form of A. But to get null space, we need to have the matrix in reduced echelon form, but it is not in reduced echelon. For that, we need to have 1 here. In reduced echelon form, the pivot positions must be 1. So I am dividing with 2. The second row is divided by 2, so that I can get 1, 5 by 2, 3 by 2. Now it is in reduced echelon form. So the equivalent equations are x1 plus 6x3 plus 5x4 is equal to 0, and x2 plus 5 by 2 x3 plus 3 by 2 x4 is equal to 0. So the general solution is x1 is minus 6x3 minus 5x4, and converting the equations like this. X2 is equal to minus 5 by 2 x3 minus 3 by 2 x4 with free variables x3 and x4. These two are free variables. Now the vector x1, x2, x3, x4 is x1 is this one minus 6 x3 minus 5 x4, and x2 is this one minus 5 by 2 x3 minus 3 by 2 x4. x3, x4 are free variables. So this can be written as x3 times minus 6 minus 5 by 2 and 1, and this is 0, plus x4 times this is minus 5 minus 3 by 2 and 0 and 1. So let us name it as u and v. Then this can be written as x3u plus x4v, where u is equal to this vector minus 6 minus 5 by 2 1 0, and v is this one. So every linear combination of uv is in null space A, as we have seen earlier, and uv is the spanning set of null A. That is, null A is equal to span of uv, that is span of these two vectors. Further, we can observe that these two are linearly independent, since one is not a multiple of other. So linearly independent and spanning null A. So since both the properties are fulfilled, we can say that this is a basis for null A. So first, I can simplify these vectors. Instead of having a fraction, I can multiply with 2 and minus 2 of course, so that I can get 12, 5, minus 2, 0. And here it is 10, 3, 0, minus 2. Let us check whether these answers are correct or not. So this is the matrix. These are carried here. Now taken A here. All the entries are posted here. And these two are my vectors in the null space A. So if I am taking 1 and 1, this is the resultant vector. If this is posted here, I am getting a 0. Similarly, any combination, you can 6 and minus 13. This is a new vector. If this is multiplied with this one, I am getting zeros. So these two vectors form a basis for the given matrix A. If I change this, change any other vector, I am getting 3. It is not a 0 vector. So it is a model for 3 by 5, but here we have only 3 by 4. That's why the fifth column is kept zeros. Similarly, here also fifth row is kept zeros. We have only 4 entries here. So in the earlier model can be placed for this also by putting zeros in the extra columns. So So this is the model for that. So you can also do experiments with the Excel sheet to understand the nature of the task. Let us go back to. So this is the basis for now. So these are the some of the problems on basis of null space A and null space A. With this, let us conclude this class. Thank you for watching.